Okay, hello, welcome to my channel. Now in this video, we're going to get familiarized, alright, with the binomial theorem of expansion. Good. Okay, so let's have a binomial that is sum of two terms where this could be even numbers, alright, raised to some power. And let's assume that the power is a non-negative integer, right? That means we start off with 0, right? So let's see. When the power is 0, let's say a plus b raised to the power of 0, of course, we know that this is just equal to 1, okay? Because if you have a non-zero number raised to the power of 0, the result will be 1. Good. Okay, so let's assume that the power here is 1, and let's see what we get. We'll raise this term to the power of 1. We'll just get this term back, all right? And I'm not just going to write a plus b. I'm going to write a together with its coefficient as 1. That is 1a plus 1b. Okay, so then with the power be 2. So we have a plus b raised to the power of 2. Okay, we can expand this by multiplying a plus b by itself. Alright, that's what it means traditionally by a power of 2. When we expand, we'll get 1a squared, okay, plus 2ab plus 1b squared. Good. Okay, for the power of 3, we'll get, let's see, a plus b raised to the power of 3. When we multiply a plus b by itself 3 times, or you can say a squared, using this result, multiply this by a plus b. When you expand that, you're going to get 1a to the third power plus 3a squared b plus 3ab squared plus b to the third power. Good. Okay, maybe let's do it for the power of 4. So this will be, when we multiply this, well, this is going to be 1a to the fourth power plus 4a to the third power b plus, let's say 6a squared b squared plus 4ab to the third power plus b to the fourth power. And the coefficient of b to the fourth power here is just 1. Good. Okay, so let's do it one more time for the power of 5. When we get the power to be 5, this will be 1a to the fifth power plus 5a to the fourth power b plus 10, okay, 10a cubed b squared plus 10a squared b cubed, okay, plus, let's say 5ab to the fourth power plus 1b to the fifth power. And maybe we can continue. Alright, but let's just pause here and then observe. Good. Okay, so let's start off with the coefficients. So the coefficient here is just 1. This is the coefficient of a plus b raised to the power of 0. In fact, a coefficient maybe you can think about just 1. In fact, let's just do that. So maybe I will make a table which will contain our powers and then our coefficients. So let's have a table like this. Okay, this stands for powers, a column for power, and then for coefficients. Okay, so when the power is 0, okay, so let's see what we'll get. Then we'll go for when the power is 1, when the power is 2, and so on and so forth. So when the power is 0, we'll just have 1 out. When the power is 1, we'll have the coefficient to be 1 and 1. So when we put 1 here and then we put 1 here. When the power is 2, the coefficient are the 1 for the first term, 2 for the second term, and then 1 for the last term. Okay, so when the power is 3, we'll get 1, 3, 3, 1. Of course, I know that because I saw it here. Not really because I saw it here, because I know it already, right? And yeah, a lot of you can agree with me on that. Okay, let me see. When the power is 4, we get 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. Maybe you can even see where we are going. Just like saying, add 1 to 3, you get 4, 3 plus 3 is 6, and then 3 plus 1 is 4, and then we'll always start off and end with 1. Good. So for the power of 5, the coefficients are 1, 5, 10, 10, 5, 1. And that agrees with what we have from the expansion. So those are the coefficients. So you can use that to generate as many as possible, right? But what happens for an arbitrary non-negative integer n, right, where n can even be 100, and we don't have to do this up to 100 times to get there? So what do we get for, let's say, the general form, okay, for coefficients of this? And in fact, it's not just enough to know the coefficients, it's also enough to know the terms as well. So let's see, let's observe something. So we notice that for the power, let's start off with the power of 2, right? So for the power a plus b raised to the power of 2, for the coefficient we've talked about it at least, let's pause here. But for the powers, well, you notice that for the first term, a takes the entire power, which is power 2. For the second term, a times b, the power of a has reduced from 2 to 1. Meanwhile, there was no b here in the first term, which means the power of b must have been 0. So the power b is now here with the power of 1, which means that the power of b has increased from 0 to 1. Meanwhile, the power of a has reduced from 2 to 1. Okay, then for the third term, there's no a again here, which means that the power of a there is 0. So since the power of a here is 0 and the power of b has increased from 1 to 2, so it looks as if for each term, the power of the first term reduces from the entire power down to 0. Meanwhile, the power of the second term increases from 0 to the entire power. So you can observe that for the third term. You can observe that in the expansion of the third power. You can observe the same thing over here. So the power of a starts off with 5 and ends with 0. Meanwhile, the power of b increased from 0 up to 5. Good. Such that for each term, the sum of the powers of these terms here, for each term, the sum of the powers of these numbers here, or those terms, add up to the entire power. Like 3 plus 1 will be 4, 2 plus 2 will be 4, 1 plus 3 will be 4, and then 0 plus 4 will be 4. Same thing over here. Okay, and that makes sense, right? That's very interesting to know. So with that, we can have maybe a general form. And we may not really be sure of this. It's just based on observation, but we will have to prove it, right, to be sure, yeah, that is true. Good. So let's say for any power n, that this can be written in a general form, okay, with the expansion of this as, since it is a sum of all these terms, so we start off with the sigma notation, the sum. Okay, maybe let's use some index. So let's say we use r, as r starts from 0 up to n. All right. Now, notice that for power of 1, there are 2 terms. For the power of 2, there are 3 terms. For the power of 5, there are 6 terms. All right? That means that for the power of n, there will be n plus 1 terms. So let's start off with 0. We are starting with 0, we end with n. In other words, there are n plus 1 terms, because we start off with 0, you have a term with r as 0. When r gets to 1, there are 2 terms. When r gets to 2, there are 3 terms. When r gets to n, there will be n plus 1 terms. All right, so that's why we end with n here, where this n is a non-negative integer. Good. Okay, so the next thing we should consider should be the coefficients, because we are going to be adding terms, and each of these terms have coefficients. So what should the coefficient look like? Maybe I'll pause there for the coefficient. Maybe let's have a bracket like this, and then let's talk about the power. So you observe that as the power of the first term reduces from the entire power down to 0, the power of the second term increases. So maybe you can have something like, for this a, we will have a, okay, it will be reducing, which means starting from the entire power, it will be reducing. So we subtract r, so that when r is 0, this will be n minus 0, which will be the entire power n. When we are done with that, we enter r to be 1. This will reduce by 1, all right? And then the second term will be increasing as r increases. That means this will be raised to the power of r. Good. So maybe you can test that for the power of 3 to see, or using the power of 3 to see if it makes sense. With powers only, not coefficients yet. So when the power is 3, the entire power here will be n here will be 3. That means we are going to have 4 terms, all right? So when the power is 3, it will be a raised to the power of 3. When r is 0, 3 minus 1. Sorry, 3 minus 0, that will be 3. b raised to the power of 0, that produces this term. Then when the r gets to 1, to now be plus the coefficient, which we are here to determine, then a raised to the power of 3 minus 1, which will be a raised to the power of 2. b increases to 1 when r is 1. When r is 2, a raised to the power of 3 minus 2. 3 minus 2 is 1, that's why the power of a is 1. And then b raised to the power of 2. And then the last term follows as well. Okay, that makes sense. So what about the coefficient? We've been keeping that. Well. It's just our observation of a kind of sequence that is produced by combinations, all right? So let's say we want to know the number of ways, or a number of ways of choosing a particular number of objects from a given sample, or from a given set of objects, all right? So let's say we want to choose a team that consists of 2 players given 5 different players. Good. And in this selection, we don't care about the order in which the players are chosen. For example, if we choose player A, maybe out of 5 different players, say from players named from A to E, if we choose player A and choose player B, then it does not matter whether we choose A and B or whether we choose B and A. Provided we've chosen A and B, we have players A and B in our team, right? That is one selection. Good. So in how many ways? So let's say we have 3 things to choose from, right? So in how many ways can 3 things be given to one person? Or, sorry, this one is the power when r is 0. So in how many ways can 3 things be shared to nobody? All right? There is only one way, and that is by doing nothing, by not sharing anything. So that makes the coefficient here to be 1. Maybe let's use this out. That makes the coefficient here to be 1. Good. So let's consider another way. In how many ways can 3 different things be shared to one person? Okay, let's say you want to share, we have 3 different books, and you want to share it to one person. Okay, there are 3 ways: either you give the person this book, or you give the person this other book, or you give the person this other book. So there are 3 ways in which 3 books can be shared to one person, and that's why we have 3 here. 1, 3, 3, 1. Then this one will mean how many ways can 3 different books be shared to 2 people? Good. So let's see. If you have 3 different books, you want to share it to 2 people, or let's say you want to form a team. You have 3 players, you want to form a team of 2 players. There are 3 ways of doing that. Is either you choose player A, if the 3 players are A, B, and C. Either you choose player A and B, or player A and C, or player B and C. Alright? So there are 3 ways. That's why we have 3 here. Then lastly, in how many ways can a team of 4 be formed from a team of 3 be formed from 3 players? There are only 3 ways. Alright? There's only one way, sorry, to form a team made of a team of 3 players, and you have only 3 players. Just pick the 3 players, right? There's only one way of doing that, and that makes sense over here. Okay, so if you also want to analyze that using, maybe you have 4 different things to choose from. Okay, you don't want to choose anything. There is only one way by doing nothing. You want to choose only one thing given 4. There are 4 ways. Okay, you want to choose 2 things given 4, and if you want to look at that based on combinations, it makes sense, all right, where the order does not matter. So this kind of sequence can be generated by that, and that's exactly what I'm going to use here. I'm going to say n, choose r. Okay, so when r is 0, we know what we'll get. N combination r as 0 is going to be just 1, and that chooses the first term. So if you can test this for each of these powers, you see that this works. And we'll not just stop here. We're going to go ahead to prove that whether this is true or not, right? And we'll hope for the best. Maybe if you're not used to this notation, just know that this notation here, n r, then in long bracket like this, same thing as saying n combination r, which has a formula as n factorial over n minus r factorial divided by r factorial. That means that that means the number of ways in which r different things can be chosen from n unlike things will be this, and this is possible. We divide it by r factorial because the order in which those things are selected or chosen does not matter here. Good, like I illustrated using forming a team from a certain number of players. Okay, great. So what we'll be doing here, I'll clean everything on this board, and then we are going to prove that this right here actually gives us the expansion of this term, right, for any non-negative power n. Okay, so let's just clean it and start off with the proof. Okay, now we're ready to prove that this is true, right? And we're going to be using, of course, the principle of mathematical induction, that's the PMI. Okay, so you notice that I've given this a name. I call it P of n, which is more like a propositional function depending on n, okay, where n is a non-negative integer. So the base case there will be 0, okay, when n is 0. So for principle of mathematical induction, we start off with the base case. That is as a way of verifying whether it's true. That is to even know whether you should even do anything at all. So you start off with the base case just to check whether everything will work for the base case. So when n is 0, all right, which is the first element in the set of non-negative integers. So when n is 0, what happens? Will the left hand side and the right hand side be the same? So we're going to replace a plus b, sorry, we're going to replace n here with 0 on the left hand side. So a plus b raised to the power of 0, the result will just be 1. So we have 1 there on the left hand side. So let's see what the right hand side will be. Well, when n is 0, we're going to have the sum as r start from 0 to 0. In that case, there is no sum, right? It's just going to be a single term, and that will be the when r is equal to 0 term. And we're going to substitute n to be 0 as well. So that will be 0, 0. So 0 combination 0, which will be 0 factorial, divided by, that in place of n factorial, divided by n minus r factorial, that will be 0 minus 0 factorial, then r factorial, that will be 0 factorial, right? Then we multiply it with, well, a raised to the power of 0 minus 0, that will just be 1, right? And then b raised to the power of 0, that is still 1. So of course, let's determine this. Let's just hope it's going to be 1 as well, so that we can put the equality sign like this, right? But right now, there's no equality sign there. Okay, great. So you notice that 0 factorial is 1 divided by 0 factorial is 1, 0 factorial is 1, so everything here will be 1, and that works. Okay, so we say 1 equals to this, and this is equals to 1. Yeah, that's why we say 1 equals to this. So that is true for the base case. Okay, maybe you can put here P of 0 is true. That is P of n is true when n equals to 0. So P of 0, okay, is true. Good. Okay, that is the verification we verified using the first element in the set. Now let's go on to the induction hypothesis. by the induction hypothesis, we're going to prove that we're going to check, or sorry, we're going to assume that the statement is true for some arbitrary non-negative integer, and then we are going to use that to check, or to check whether it is going to be true for the next non-negative integer. So we say assume that for some k, that p of some non-negative integer k is true, okay, where this k is an integer greater than or equal to, let me put it this way, it belongs to the set of integers greater than or equal to 0, something like that. All right, good. So we show that we assume that this is true for this kind of element in this set of integers greater than or equal to 0. Okay, so in that case, that would mean that when we raise the left hand side to the power of k, where the right hand side it will give us the right hand side where n is replaced by, where n is replaced with k. So that will be a plus b raised to the power of k. This is equal to, well, let's see, that will be the sum. Okay, this is going to be the sum as r start from 0 to k. So we say where n is replaced with k, then k combination r. Okay, then we have a raised to the power of k minus r, then b raised to the power of r. Good. Okay, so we've checked that. Maybe let's call this a name. Let's call this equation, let's just put it as an asterisk. Okay, that is from the assumption. So you notice that the principle of mathematical induction is like a kind of casino stuff. It goes this way. You start off with some small stuff, then you now use that to show that the next one will be true, and then you now use that to show that the next one will be true, and so on and so forth. So we are using this k as some arbitrary element in the set of non-negative integers, which we use as our powers. And then we will have to show that using this k, we want to show that the next one will be true. Okay, good. So we assume that it is true for this one. We want to show that the statement when n is k plus 1, that is p of k plus 1, we want to show that when n is k plus 1, this statement will also be true. All right, it's also true. Okay, so what does that mean to say p of k plus 1 given p of n? So you just replace n with k plus 1. That's what we've done. So that's exactly what we're going to do for each of these. But in this case, we'll start off with one of the sides, and then we'll show that it implies the other side. So let's have a plus b raised to the power of k plus 1. Good. So we're going to use some indical properties on that. There is some indices on that. This will mean a plus b, all right, times a plus b, but this other a plus b will be raised to the power of k. So that's how to rewrite that. But we notice that from equation star, we can replace this, all right, with what we get from equation asterisk. That a plus b raised to the power of k can be written using this sum. So this left hand side will become a plus b times, now a plus b raised to the power of k. That would mean this thing right here. That would be the sum, okay, as r starts from 0 up to k of, let's put it down here, k combination r, a raised to the power of k minus r, then b raised to the power of r. Good, great. So let's use the distributive, let's distribute. So we're going to multiply this by a and then add it with multiply it by b. So that will be a times that sum. In fact, let's write it out. Let's write this. So you notice if you multiply this sum by a, okay, this a will increase the power of a in there. That means you're going to have the sum as r starts from 0 to k of the combination k choose r. Then we have a raised to the power of k plus 1 minus r. So I've increased the power of a by 1, all right, using the fact that the power of a here is 1, and then we put the b to the power of r there, then we distribute. So we also use b to multiply. So similarly, we're going to get b, for the one of b, this will be k choose r, a raised to the power of k minus r, then b raised to the power of r plus 1. Good, that's because we've increased the power of b by 1. Okay, so let's see what we can do next from here. Well, what I will do here is to try to combine these two sums again. I mean, why did we even scatter it, right? And by combining these two sums, we want to get this this term, this is b raised to the power of r plus 1. This is b raised to the power of r. So let's get the b's to have the same power and the a's as well to have the same power to be able to combine. And that will be by replacing r here. We replace r with, so let me put it down here, replace r with r minus 1. So when we replace r with r minus 1, we notice r is going to start from 1 up to k plus 1. But in this case, we're going to have a raised to the power of k minus r plus 1, which is what we have over there. Then this is going to be b raised to the power of r, and that makes sense over there. But replacing r with r minus 1, of course, I said it earlier that this will be r starting from 1. So we need to evaluate the r being 0 here so that we can start with 1 as well. So everything will rhyme. In that case, when we evaluate when r is 0, this will be, well, substitute r being 0. That will be k choose 0. Well, that would just be 1. So we have 1 times. Now when r is 0 here, that will be a raised to the power of k plus 1. Good. Then b raised to the power of 0, which is just going to be 1 times that. So this stays. Then we add it with the sum. Okay, when r now starts from 1, since we've evaluated the 0, then we'll have k choose r, a raised to the power of k plus 1 minus r, then b raised to the power of r. Great. Okay, so over here we do the replacement, replace r with r minus 1. This will be the sum. Well, if r starts from 0, r minus 1 also starts from 0, which means r will start from 1. Good. Then we take it to, when r is k, r minus 1 will be k, that means r will be k plus 1. So let me put it out here, k plus 1. Okay, then this is going to be, well, replace r, this is k, r is r minus 1. That's what you replace. A raised to the power of k, a raised to the power of k minus r. So replacing r with r minus 1, that will be k minus r minus 1. That will be k minus r plus 1. So maybe I can rewrite it as k plus 1 minus r. Then b raised to the power of r plus 1. R is replaced with r minus 1. That will be r here. That's very nice, isn't it? So you notice that for the sum index, we start with 1. We start with 1 here. And then the terms, apart from the coefficients, the terms stays the same. So we can combine these two sums here. But notice that this one ends with k plus 1, which means we are going to take the k plus 1 term aside and add it separately. So this is going to be just like we did for this one by evaluating this when r is 0. So this is going to be k plus 1 here. Plus, so we'll combine the sum. So we take the sum as r start from 1 to k. All right, so let's see what we have. Well, like I said, we want to combine these two, which means we'll have k choose r, okay, plus k choose r minus 1. By doing that, we notice that this and this are the same, though we are going to evaluate it when r is k plus 1, because this one stops at k. So this is going to be a raised to the power of k plus 1 minus r, b raised to the power of r. Then we add it with, okay, so when r is k plus 1, what happens? So we're going to substitute k plus 1 in place of r in this term. Okay, so let's see what we get. In place of r, you could put k plus 1, that'll be k. Well, in place of r, you put k plus 1, so maybe we can just do it and see what we get. K choose k plus 1 minus 1, that would be k. So k choose k, right, is just 1. There is only one way of choosing 5 different things out of 5 different things. There's only one way, by choosing each of them and all of them, right? Good. So that's 1 times a raised to the power of k plus 1 minus r, but r is set. Let's evaluate it when r is k plus 1. So that'll be k plus 1 minus itself, which means the power of a there will just be 0. Then times b raised to the power of, well, that will be k plus 1. So everything here I can clean it. Okay, so that's just what we've added. Good. Okay, so we have to simplify this right here. So let's simplify this and see, put it back into the sum. So then let's have, now k choose r means k factorial divided by k minus r. Okay, I think I still have a little more room. R factorial. Then we add it with this other one where the r is replaced with k minus 1. That will be k factorial divided by k minus r factorial. But this will be k minus r minus 1. So that will be k minus r plus 1 factorial, then r minus 1 factorial. Okay, so let's see what this will give us. Well, we notice that these denominators, when we expand this one using the definition of the factorial, we're going to get k minus r plus 1 times k minus r, which will agree with this. Then for this other one, we can expand this other one, r times r minus 1, which will also agree with this. So we can write this as maybe we can write this as k factorial divided by, okay, so let's expand this r factorial. That will be k minus r factorial. Then for the r factorial, you can have r times r minus 1 factorial. Good. We add it with, well, you notice for this other one, we have the k factorial out here divided by this term. We're going to expand it using the definition of a factorial. This is k minus r plus 1. Okay, k minus r plus 1. Then we multiply it with k minus r factorial. Then this one stays the same, r minus 1 factorial. Okay, so now to combine these two fractions, we need to make sure that the denominators are the same. Good. So to make sure that this has the same denominator as that, we need to multiply this bracket by, we need to multiply top and bottom by k minus r plus 1. So maybe let me multiply this by k minus r plus 1. And then this one, we need to multiply this one by r. So we multiply that by r. So by doing that, we can combine these two fractions. So maybe let me clean this part of the board, then we'll continue working with this. Okay, so let's combine. Since the denominators are now equal, the denominators are equal because we just did multiplication by 1. I don't want to multiply the denominator, but that's a trick we can use. So let's see what we get. So that will be k factorial times k minus r plus 1. We add it with this other one here, that is k factorial times r divided by, well, let's see, the denominators will be k minus r plus 1 times k minus r factorial times r minus 1 factorial. So what we've done is that this term will come to the denominator as well, and that will repeat. This term will come to the denominator as well, so all the terms will be there. That is 1, 2, 3, and then let me see, 1, 2, 3, and then 4. Yeah, that's what we have down there. Good. So you notice that the thing is common here, and that is k factorial. So if you factor out the k factorial, okay, we are going to have k minus r plus 1 plus r. That would be k plus 1. So we have k plus 1 at the top. Well, divided by, let's see what we have in the bottom. Well, at the bottom, maybe we can, let's see how we can combine this right here at the bottom. Okay, so at the bottom, well, let's see. This is k plus 1 right here. So if we have m factorial, m plus 1 minus k, m plus 1 minus r, okay, that's it right there, then r factorial. So okay, so let's see what we get at the bottom. Well, notice that maybe I can rewrite this again, k minus r plus 1 times k minus r, that is just k minus r plus 1 factorial. So we have k minus r plus 1, okay, factorial. Then we have r times r minus 1 factorial, that's the same thing as r factorial. In fact, the top, this right here is just k plus 1 factorial, alright? That is k plus 1 factorial. How do you know that? This is k factorial times k plus 1. So that must have been the expansion of k plus 1 factorial. That will be k plus 1 times k factorial. Okay, that's what we have over there. So that means that this place, this coefficient, the sum of these two coefficients, simplified to k plus 1 factorial divided by this denominator, of which that could be understood easily to mean k plus 1 choose r. All right. So maybe let me rewrite it for you to see. This is k plus 1 factorial divided by, let's put the k plus 1 first, k plus 1 minus r factorial, which means we are going to have k plus 1 choose r in the combination. So how do you know that? This is k plus 1, you put it out here, k plus 1 factorial in place of the n factorial divided by n minus r, that will be k plus 1 minus r, then r factorial. So this is what we have. Good, so this adds up to that. So that that sum will now become, well, let's put the first thing we have here, that will be a raised to the power of k plus 1. So let me put it out here, a raised to the power of k plus 1. So we're going to write this sum, but replacing this right here with that because we've shown that that's what it is. So that will be the sum as r starts from 1 up to k, okay? So r starts from 1 up to k of this term added to give us that. So let me put it out here, k plus 1 r, that is a combination, k plus 1 choose r terms. Good. Then we have this right here, that will be a raised to the power of k plus 1, a raised to the power of k plus 1 minus r, b raised to the power of r. Then we add this other term, b raised to the power of k plus 1. Good. So this sum has all of this. Good. Okay. Now this is what we'll do. Recall that we got the a to the power of k plus 1 by expanding this sum when r is 0. And then we got the b raised to the power of k plus 1 by expanding this sum where r is k plus 1. That was what we had over here. So after replacing, we had to evaluate it when r is k plus 1 to get the b raised to the power of k plus 1 term. We had to evaluate this when r is 0 to get the a raised to the power of k plus 1 term. So we are going to bring back all of those things. That would mean we are going to have the sum as r start from 0. From 0 means we are going to bring this thing inside it, all right? And then up to k plus 1. The k plus 1 means that we are going to bring this other term inside it. So everything will now turn out to be the combination. That will be k plus 1 combination r, a raised to the power of k plus 1, all right, minus r, then b raised to the power of r. And that's it. So this is what we'll do to know if we were actually proving it. So we are going to highlight this k plus 1 term, okay, and check if it appears where n is supposed to appear. That is k. Okay, great. So let's observe. This k plus 1 in red, does it take the position of n in the actual thing? So that is n over here. Of course, that's k plus 1. Then k plus 1 choose r, n choose r, a raised to the power of k plus 1 minus r, a raised to the power of n minus r, then b raised to the power of r. So that works. Okay, that means that this right here is true as well, which means that we've shown that by principle of mathematical induction that this statement, which we call p of n, is true for every non-negative integer n. Great. So that is actually the theorem. In fact, this is what the binomial theorem tells us. And with that, we can maybe get some very nice or wonderful properties from that. But that is very nice. So we've actually observed the formula, okay, and then we've proven that this is true using the principle of mathematical induction. All right. Okay. Thanks for watching. Please share this video with your friends, and of course, we are going to continue from our next video. Not continue. We're going to see in our next video. Thanks for watching.